Good morning, everybody. I am Marita Kotze, the Education Specialist for Physical Sciences at Impact. And we're going to give the attendees a minute or two so that everybody can log into this webinar. A very big welcome to you and thank you for attending the webinar this morning. I'm very excited to talk to each and everybody of you today. So yes, I will deal with your questions afterwards. If you do have any questions for me, so you can at this stage you can download the handout while we're waiting. It's the webinar but presentation. So make sure that you download it. So I can see just Okay, while we're waiting, I hope, sure, the sun is. All right, I'm going to start. I think everybody logged in already, so yes. Okay, I'm going to start the session. Again, my name is Marita Kotze, Senior Education Specialist for Physical Sciences at Impact. Before we begin with this webinar, let's cover some of the basics. If you're struggling to hear me, make sure your audio is on and your speaker volume is turned up. You will be automatically muted when joining this session. I'm not going to answer any questions during this session, but if you do have any question, you can write it in the question box below or to your right. To raise your hand, you can click on the icon on your dashboard below to the right. Let's just see. All right. While attending this, thank you. All right. You can download this presentation and additional resources in the handout box below or on your right. You will also find all this information in the question box. Remember to send me your questions, write it in the question box. You can send me your questions to academics@impact.co.za or to info@impact.co.za. And visit the Impact YouTube channel for recordings of the session. The PDF of this session will also make it available on the Impact learning platform. Okay. All right. We are. I'm doing the matter and materials knowledge area today and intermolecular forces. All right. So intermolecular forces and interatomic forces, and also the influence of intermolecular forces. The reason why I choose this area today is because I only did one slide previously in a webinar, and this is one of the most important parts of chemistry that you use in grade 11 and grade 12 to explain reactions, chemical reactions. So make sure that you do understand the intermolecular forces. You can see that you can also use my PowerPoint as notes. I give a lot of information into the notes. So make sure that you do understand it and that you can use it to explain this. All right, just the sun. Okay, intermolecular forces give the reason to cohesion in water molecules. So this is the attracting forces between molecular units which keeps molecules together in a liquid or a solid. Inter means forces between the molecules. So it's between the molecules. So this is very important. So we talk about forces. That's the thing we're going to talk about. Okay. We did cover different bonds previously in a webinar, the polar bond and the ionic bond, metallic bond. So today we're talking about the intermolecular forces for these different bonds that you did previously. All right. The polar you have a polar covalent bond and a non-polar covalent bond. All right. The polar covalent bond do have can form dipoles. All right. Or it forms dipole. It makes a polar molecule. So we also say it is a dipole. More of that later on in this PowerPoint presentation. So we have either between a polar covalent bond and a polar covalent bond, we have dipole-dipole force. So for example, polar covalent molecule, we have dipole-dipole forces because the polar covalent molecule is a dipole and the polar covalent molecule is a dipole. So therefore, we can have dipole-dipole forces, for example, water. Then we have, when we want to dissolve sodium chloride, which is stable salt, when we dissolve it into water, the table salt is a ionic bond, and the moment when table salt dissolved into water, it forms ions. Okay, so the ions that's in the water, there are forces between the sodium, positive ion, the chlorine ion, and the water molecules, which is polar covalent. So then we say it's ion dipole forces. All right. Then we have ions and non-polar covalent bonds. All right. The only way that non-polar molecules and ions can dissolve in each other, it is with if there's an induced dipole. More of that then later on. And if it's non-polar and non-polar, then we have induced dipole forces. All right. So atomic bonds that we did with covalent bonds, ionic bonds, metallic bonds. We have our covalent bonds is where a hydrogen share his outer shell electron with a carbon and another hydrogen and another. So this is all about sharing. Your covalent bonds is all about sharing. This molecule is a non-polar molecule. Can you see they are all around the carbons are hydrogens. There's a covalent bond between the carbon and the hydrogen, and the covalent bond between the carbon and one hydrogen is polar, but in the whole the molecule is non-polar. All right. As I said, we have the ionic bond, sodium chloride, which is stable salt. For the table salt to dissolve into water, we have sodium, that a sodium ion and a chlorine ion that is in a crystal that forms a giant crystal lattice. So the giant crystal lattice and the electrostatic attraction forces between the sodium and the chlorine ions in the giant crystal lattice must break in order for it to dissolve into water. The other is the metallic bonds. Metallic bonds are delocalized electrons around positive atomic rests. Okay, so intermolecular forces, if we look at it, we say it's the different attracting forces between ions and molecular units, which keeps molecules and ions together in a liquid or a solid. So we have the particles that we do have are the ions. Now, ions are connected together with strong Coulomb forces, Coulombic forces, or electrostatic forces. And we have ions and polar molecules, and it will be an ion dipole force. Two polar molecules will be dipole-dipole forces because it's two dipoles that are attracted to each other, like a water and a water molecule, sodium ion and a water molecule. Ion and non-polar molecules, like for example, if we want, if we have water and if we have oil that's non-polar and we have iron, so polar, the force that with the type of force, it's ion-induced dipole. Polar and non-polar molecules are dipole-induced dipole. Non-polar molecules are our weakest forces, and we also say it is London forces, London van der Waals forces. More about that. Okay, so we are talking about ion dipole, ion-induced dipole, dipole-dipole, dipole-induced dipole, and hydrogen bonds. Now, the first two are intermolecular forces involving ions because of the ions in it, and then van der Waals forces are the dipole-dipole, dipole-induced dipole, and we have hydrogen bonds. All right. So the first one that I want to explain is the ion dipole force. That is where we dissolve the sodium chloride, which is stable salt, in water. It's therefore a positive sodium ion that wants to dissolve in a dipole. The reason for a dipole is that we have a, if you can see here, we have on that side, we have a more negative side because of the lone pairs of the electron of the oxygen atom, and the hydrogen share the two orbits that only have one electron. So therefore, that side is the positive side, and the hydrogen atoms with the lower electronegativity forms the positive side, and the oxygen with the high electronegativity forms the negative side. So what is happening here is a force of attraction is between the polar water molecule and the sodium ion. The polar water molecule and the sodium ion. Can you see these? All of them, they are water molecules. If you want to dissolve, they dissolve in water. So the sodium ion will be connected with the negative side of the dipole. So all of the water molecules will arrange itself around the positive sodium ion with the negative side of the hydrogen molecule. So a positive ion will attract the negative pole of the dipole. So that's why we say the bond between the sodium and the water is an ion dipole intermolecular force. Right. So an ion-induced dipole. So here we have oxygen. Now oxygen is a non-polar bond. It is a diatomic molecule in nature, so it's a non-polar bond. So there are no poles in oxygen. Right. So what is happening if we have a non-polar molecule and we have an ion? Here we have iron, that's a 2 positive ion. So an ion induces, therefore, if the ion needs to be exposed to the oxygen and there must be a contact, a force between the two of them, then the intermolecular force, something must happen, because if it's non-polar and it's not a dipole, so it cannot connect to it. The only way it can connect to it if the oxygen molecule do have any poles, like a positive or negative side. So what is happening here with oxygen is there's an induced dipole. So the positive ion induces a dipole in a polar molecule, in this, either in an atom or a polar molecule. And in this example, it's oxygen that's a non-polar molecule. All right. So when it's a non-polar, it must be non-polar. When the ion comes close to an oxygen molecule, an induced dipole occurs on the oxygen molecule, which is a non-polar molecule. So the strength of this induced dipole depends on how easily the electron cloud around the atom or polar molecule can be distorted. All right, how easily? So that will be, the bigger the molecule, the stronger is the induced dipole. All right, so the dipole-dipole forces, it's easy. If it is a dipole molecule, the intermolecular force that occurs between the polar molecules is dipole-dipole. It's hydrogen chloride do have, again, a positive side and a negative side. Chlorine does have the higher electronegativity. Therefore, the chlorine side is the negative side and the hydrogen is the positive side. So the dipoles will connect to each other with the negative side and the positive side. It arranges around each other so that it's a negative and positive attract each other. All right. So the dipole-dipole force. This is a dipole-dipole van der Waals force that you find here between the dipoles. All right. Another one is the hydrogen bonds are a specific type of dipole-dipole force. Hydrogen bonds are very strong bonds, so it is a specific dipole-dipole force. Right. So now another van der Waals force is a dipole-induced dipole. Here we have again the hydrochloric dipole molecule. That's a polar molecule. That's also a dipole. And argon is a noble gas. Now noble gases don't have it's in a noble gas. It does have the right number of electrons in the outer energy level. So the polar molecule induces therefore a temporary dipole in an atom or a non-polar molecule. All right. So here we have another example of water and oxygen. If you want to make hydrogen peroxide, to have another oxygen atom in the hydrogen peroxide, so then something must happen, but it must attract each other in any case. So the water molecule again arranges itself so that it can connect with the oxygen molecule, but the oxygen molecule there's no dipoles. All right, it's a non-polar molecule. So what is happening here is a dipole must be induced in the oxygen molecule. Again, it forms a positive side, so all the electrons move to that side, because at first there is a, between the negative and the negative side, there is a repulsion between the two molecules, and then some of the electrons move to that side of the molecule. Therefore, this side becomes positive. That's why we have an induced dipole here, and it can attract each other. It is the same way here. If we have an argon atom, the electrons will move to that side of the atom, or to this side of the atom. So if it is next to the hydrogen, which is positive, the electrons will move to this side. If the argon atom is next to the chlorine side of the dipole, the electrons will move to the other side, so that the positive side of the argon atom is next to the negative side of the chlorine. Okay. Now, what is London dispersion forces? This is the weakest van der Waals forces, and this is where intermolecular forces between two nonpolar molecules that form temporary dipoles. It's nonpolar, therefore here we can see neon and neon, both of them are noble gases, don't have any, and it's not no polarization. They don't share any electrons because they do have the correct amount of electrons in the outer shell. So the only way that neon and neon can form a bond must, for it to form an instantaneous dipole, must be created. An instantaneous dipole must be created, and again, the way an instantaneous dipole is created is it repulses each other in such a way that a certain part of the atom becomes positive, and the other side, the electrons, because remember, it does have the correct amount of electrons. So there's no place for any electrons. So the repulsion must be in such a way that the electrons just move a bit to the side for it to form a positive side, or the negative side of an adjacent atom to attract each other. Okay, so that's why we say it's a non-polar and a non-polar, and dipoles are induced in both non-polar, and then instantaneous dipoles are created in both of them to form two dipoles so that it can be attracted to each other. All right, now what is hydrogen bonds? Hydrogen bonds, okay, between the hydrogen and the oxygen, there are interatomic bonds. All right, between the hydrogen and the oxygen, there are interatomic bonds. All right, the moment when a water molecule and a water, if I do have a glass of water, what is in the glass of water? There are thousands, there are millions of water molecules in a glass of water. So how can I have a glass of water? There must be a bond between the water molecules to form a glass of water, because if there's the attraction is not strong enough, it will be a gas. All right, so what is happening here? It forms hydrogen bonds in order for us to have a glass of water. It forms between small, highly electronegative atoms. All right, so it must be between the oxygen of the one water molecule to the hydrogen of the other water molecule. The straight lines that you do have here, is an interatomic bond. But between the dotted line between one oxygen, the oxygen side of this water molecule, and the hydrogen side of that water molecule, that is the hydrogen bond. Okay, and this is a type of dipole-dipole attraction force, but it is much stronger than a dipole-dipole attraction force. So remember, polar molecules occur when one atom is more electronegative than the other atom. The atom with a high electronegativity is slightly negative, and the other side slightly positive. All right, so in this, it's very important. This can be also a hydrogen bond between water and hydrogen fluoride. Okay, then it will be the hydrogen of the water molecule and the fluoride of the hydrogen fluoride molecule. All right. So what do we have here? Here you can see we have intermolecular forces, intermolecular, intramolecular, and interatomic. Now, as stated in the previous slide, we have interatomic forces between the hydrogen and the chlorine atoms. These two atoms, we have a hydrogen and a chlorine interatomic forces. So it is forces that exist between two atoms. Now, what is intramolecular bonds? The interatomic force is also, the name for that is also, we also say it's intramolecular because it's inside the molecule. It's intra, it's inside the molecule. Here we say also it is an intramolecular bond. Okay. What is intermolecular force? Hydrogen bonds are intermolecular forces. It's between the oxygen and the hydrogen. So intermolecular forces exist between molecules or in a molecule. All right. Sorry about this one. Moves to the moment we have PDF. All right. So it's again between the hydrogen of this side, and just to show it from another angle, the hydrogen of this water molecule and the oxygen of this water molecule. All right. Now the difference between intermolecular and interatomic forces is intermolecular is between the oxygen of the one molecule and the hydrogen of another molecule, while interatomic forces or intramolecular forces are in the molecule between the hydrogen and the oxygen. So what is the difference between the interatomic forces and intermolecular forces? It's atoms or molecules, it's forces between atoms. Intermolecular is forces between molecules. The strength of the force is interatomic forces is strong forces. Intermolecular forces are relatively weak forces, except for the hydrogen bonds. The hydrogen bond forces, the distance between the atoms of the molecules in interatomic forces, it's very short distances. With intermolecular forces, it's larger distances than bonds. All right. So if we look at the relative strengths of intermolecular forces, you will see that dispersion forces, our London forces, are the weakest forces that are because of its nonpolar and its ion. If a nonpolar and a nonpolar molecule wants to attract each other, we have induced dipole. So that's why it's the weakest. But the moment we have a dipole of a sort, and then it increases. So dipole-dipole will be a stronger force than the dipole-induced dipole, and the hydrogen bond will be more stronger than the dipole-dipole, and the iron dipole will be stronger than the hydrogen bond. So when are you going to use this? Why is it necessary for you to know this? You are going to use this to explain the forces between the and melting points and different properties of molecules. All right. So here I put in a summary of the intermolecular forces for you, the definition, the diagram, what is the difference between the London forces. It's because hydrogen gas and hydrogen gas, it is a temporary dipole that forms in order for them to attract each other. So the attraction between the instantaneous dipoles is asymmetrical, and it's all atoms and molecules. The relative strength is weak, it's the weakest. The other information is increase in strength as the molar mass increases. These are the information you're going to use. You first have to decide if it's a dipole or if it's a two induced dipoles that means that attract each other. So that will depend. You first decide, or if you get to a question, you see what type of molecules do you have. So the moment you have hydrochloric acid and hydrogen gas, you will see, okay, or hydrogen chloride and hydrogen gas, you will see, all right, I have here a dipole, but there's an induced dipole. So this force will be immediately a stronger force than the force between the two temporarily induced dipoles. But if the molar mass increases, the strength of the London forces increases. Right. The London van der Waals forces. Right. So the dipole forces is attraction between two permanent dipoles. We have two polar molecules. Medium strength is stronger when molecules are closer together. Right. And then the strongest one of all of them are hydrogen bonding. It's attraction between nitrogen and hydrogen, oxygen and hydrogen, fluorine and hydrogen bonds. If we have, say, for example, hydrogen fluoride and we have water, then it will be the fluorine or connects to it will be the bond between a hydrogen bond between the fluorine of the one molecule and the hydrogen of the water molecule. This is the strongest one of all of them, and it's not a chemical. It's not chemical bonding. Okay. Okay. So the influence of intermolecular forces. There are five things that we're going to discuss that does have an influence of intermolecular forces. All right. So the first one is the phase of the molecules. All right. In grade 10, we learned the heating and the cooling curve. So here we do have a cooling curve of water. So for example, so the moment we have a solid, a liquid and the forces between, this is your melting point where the solid is starting to change into liquid. This is your melting point, and this is your boiling point where the liquid changes into a vapor. During phase changes, the strength of the intermolecular changes at the same temperature. As the solid does have strong intermolecular forces, the liquid does have intermediate molecular forces, and the gas does have weak intermolecular forces. So the strength of intermolecular forces decreases as the melting point and the boiling point changes. Okay, so these are again what the type of information you need to explain the different chemical reactions. So the size and the surface area of the molecules. Okay, here we have the size. So, for example, the fluorine, I do have here the diatomic molecules, fluorine, uh, fluoride, chloride, bromide, and iodine gas, fluorine gas, no, fluorine gas, bromine gas, and iodine gas. So, what is happening here? The strength of the intermolecular forces increases. It increases as the size of the molecule increases. Okay, here you can see the relative molecular mass of fluorine is 38, of fluorine is 71, bromine 160, iodine is 254. So as the size of the molecule and the mass of the molecule increases, the intermolecular forces increases. So they can either, a question can be about the size of the molecule or the mass of the molecule. Then you can explain it that the intermolecular forces, and this is, again, this will be weak London forces because it's fluorine and fluorine. Fluorine, it is non-polar, so this will be temporary dipoles. So yeah, the strength of the intermolecular forces will increase as the size and the mass of the molecule increase. Now, what about the surface area? If we look at the surface area, here we do have a long cylindrical molecule, pentane. So there are stronger van der Waals forces because it's a very the surface area here are bigger than the surface area here. It's smaller surface areas that are connected to each other. So it will be smaller surface area, weaker van der Waals forces, but the moment the surface area are bigger, it will be larger surface areas. We have stronger van der Waals interaction forces. Now the density of the molecules here, you can see a solid, a liquid, and a gas. All right. So what is happening as the kinetic energy increases? There will be a decrease in intermolecular forces. So here you can see if the kinetic temperature decreases, the intermolecular force will increase. Right. So from a gas to a solid, the intermolecular forces increase, and from a solid to a gas, it will decreases. But so here we have a high density and a low density. So what is happening? Higher density, stronger intermolecular forces, lower density, weaker intermolecular. So what is density? It's the number of particles per unit volume. All right. So now here is two of the most important things that you need to learn is the boiling point and the melting point. I'm first going to discuss the boiling point here. Now, the boiling point of a compound is the temperature at which liquid molecules are converted into gas. Boiling energy is needed to overcome the attractive forces in more ordered liquid state. As we saw on the graph, that it will be stronger forces between the solid, and then it moves on to the gas. So the stronger intermolecular forces, the higher the boiling point. So for components with approximately the same molecular weight, remember we say it increases as the weight increases, the mass increases, okay? But if the compounds have approximately the same molecular weight, what will happen? Compounds with van der Waals forces, compounds with dipole-dipole interactions, and compounds with hydrogen bonds, it will increase the strength of the intermolecular forces. If it's the same molecular weight, you will see the one with the lowest boiling points are the compounds with the van der Waals forces, and with the highest boiling points are the compounds with hydrogen bonds, for example, water. All right. So here we have a graph. Boiling points increase with increasing molecular mass. For the group 15, 16, and 17 hydrates, the boiling points for each class of compounds increase with increase in molecular mass for elements in period 3, 4, and 5. Here you can see if you calculate the molecular if you calculate the molecular mass, you will see there are the molecular mass for hydrogen iodide is bigger than the molecular mass for hydrogen bromide. So therefore, it will have a higher boiling point than hydrogen bromide. So that's the way you're going to discuss it. When a graph is given to you, you will see you will calculate the molecular mass of the compounds given on the graph, and then you can discuss it as we discussed on the previous slide by saying that the boiling points increases with increasing molecular mass. High boiling points due to hydrogen bonds. In comparison to periods 3 to 5, the binary hydrates of period 2 elements in group 17, 16, and 15, fluorine, oxygen, and nitrogen, respectively exhibit anomalous high boiling points due to the hydrogen bonds. Okay, so where there is hydrogen bonds, water is the highest of all of them, hydrogen fluoride. Here you can see if we compare the hydrogen fluoride to the hydrogen iodide, this is a dipole-dipole force, a dipole-dipole van der Waals force, while this is a hydrogen bond, so it is a higher boiling point than the hydrogen iodide. Okay, as well as the water, that there are hydrogen bonds between the oxygen and the hydrogen of the water molecules, of two different water molecules. So therefore, the hydrogen bonds will have all of these molecules the highest boiling point. So yes, now what is the melting point? The melting point is the temperature at which a solid is converted to its liquid phase. In melting, energy is needed to overcome the attractive forces in the more ordered crystalline solid. The stronger intermolecular force, the higher the melting point. If given the same functional group, the more symmetrical the compound. All right, so what is happening here? With covalent molecules, the melting point depends upon the identity of the functional group. So what do we have here again? The compounds with van der Waals forces, compounds with dipole-dipole interactions and forces, and compounds with hydrogen bonds. Again, we have an increasing strength of intermolecular forces according to the melting point. As we see here, it will be the same as we have the boiling point. If one of them are, say for example, hydrogen bonds between our, if it's a solid, if it's ice and it turns into a vapor, the boiling point and the melting point will be, if it's a solid and it turns into a liquid, the melting point will be the highest because of the hydrogen bonds between the water molecules. The fifth and the last one is the resistance of a liquid to flow is called viscosity. So here you can see a higher number. If we do have a higher viscosity number, then you can see we have, if we have a higher SAE number, then we have a higher viscosity. and it will fall slower. For example, if we think about oil, car oil, and we compare it to water. Water flows much easier than coal. Okay, that is a thick, that does have that high viscosity. Okay, viscosity increases with stronger intermolecular forces and decreases with higher temperature. It is related to the ease with which molecules can move past each other. All right. Again, you will use this information when you do have a question regarding why viscosity increases at high if we have strong intermolecular forces, and what will happen if we increase what will happen with the viscosity of, say, for example, coal if we heat the coal. Okay, and then you have to explain it according to intermolecular forces. All right. Now again, as I did in all the other webinars, if you're not the impact learner and it's the first time that you attend this webinar, there are additional resources for physical sciences, Dr. Henshaw, Quanta books in the science clinics notes. So the Dr. Henshaw study guides that you received, if you're an impact learner, it does have summaries and mind maps. And there are also question papers available that I use as handouts up until now. There are no handouts for today except for the PDF, because some of the handout notes that we put previously on for the webinars are the question papers. The questions are included of intermolecular forces are included in that. All right. So Dr. Henshaw some exercise books that you can order from the website, as well as past exam papers. All right. The impact learners, if you did receive a quantum book this year with your package, a very useful tool for exam preparation and test preparation. Please start, if you didn't start yet, please start by doing the exam type of questions in the Quanta book. And if you do have any difficulties understanding the work, there are 2 DVDs at the back of the Quanta book. It's really excellent DVDs. Mimi Pretorius explained the most important, the key facts of both chemistry and physics, with animations, videos, and other ways, by writing and doing questions with you. So please use the DVDs if you do struggle with by understanding the concepts in your textbook. Okay, it is available in Afrikaans as well as English, so you can order it if you're not an impact learner. You can order it from Quanta Books by using this link. Okay, here is an explanation or an example of one of the exam type of questions. Here you can see a question on the concentration over time graph, the type of questions that are asked in questions and in tests and exam papers. So please make sure that you start using your Quanta book and the DVDs that you've got as tools for this year if you're an impact learner. And it's not an very expensive book. You can order it. It's between, I think, between 170 and 200 rand for the Quanta book, including the 2 DVDs. Okay, and the last thing is the smart rare books that you can download from Science Clinic's website. So please go onto the website and download the summaries. It is very important notes. You can see that it is it's very useful. there are excellent examples with the content. The content is explained, and then there are excellent examples with it. So go on their website, download the Science Clinic print books. They also do have exam seminars. They're doing also webinars now in preparation for the exam, the prelims in any case for the grade 12, and for you as well. That's going to write the exam papers, not an exam conditions, but you're going to work with that, and it's a very useful tool. So go on the website, download the prep book, and you can register for the events, for the webinars that they do. All right. So if you do have any questions, you can send an email or write your questions now. You can send an email to info@impact.co.za or to academics@impact.co.za. Thank you very much for attending today's course. I hope this was very useful for you, and that you can practice and use this content to explain. You can see, if you do the questions, you will see that how and where you use the content to explain chemical boiling points and melting points. That are your level 3 and 4 questions that are in the chemistry papers, that are 40% and 35% and 14% of your question papers. So please go on and start doing the questions in front of us to see how we answer. Thank you very much. Have a nice day.